Welcome students, I am Dr. Smita Sharma and today we will be discussing Wien bridge oscillator. So we have already discussed Wien bridge oscillator circuit that was made by the help of transistor. In that circuit we had used transistor circuit as an amplifier, and RC network was used in a special manner that was termed as lead lag circuit, which acted like feedback circuit. So here also we'll be again discussing Wien bridge oscillator using IC. Here the IC that I am using is IC 741. By the help of IC 741, I have first made the amplifier circuit. We have already discussed this amplifier circuit in detail, and we, again feedback circuit is the same lead lag circuit that we had used in the transistor circuit. So this is the basic diagram of Wien bridge oscillator using IC. This circuit has been rearranged in this way. Why I have arranged this in this manner? Because in this manner, when I arrange this circuit, Wien bridge oscillator circuit, then it looks like a Wheatstone bridge, and it is the analysis done here is very simple. It is more practical, that is, we can understand in a better way. That is why I have made it. There is no difference between this and this circuit. It is only rearrangement. So from the diagram you can see this is IC 741. The input has been given at non-inverting end. This is so this circuit is a non-inverting amplifier, and the lead lag circuit is connected between output and the non-inverting end. So this is Wien bridge oscillator. It is most commonly used audio frequency oscillator because it is very simple and it has greater stability. So due to simplicity and stability, this oscillator is used. In this circuit, feedback circuit is a Wien bridge circuit which is connected between amplifier input and output terminals, as I have shown in the figure. Now because this circuit has been made in form of a bridge, we'll be saying it is a bridge circuit. The bridge circuit has a series RC network in one arm and a parallel RC network in the adjoining arm. So if we look in this bridge circuit, in one arm there is RC circuit in series, and the parallel combination of R and C is in the adjoining arm, that is the arm that is just connected to the next initial arm. So in the adjoining arm we have this, and it is also called lead lag circuit, that we have already named it. This is lead lag circuit. In the remaining two arms of the bridge, resistors R1 and RF are connected. So this R1 and RF are the resistors that decide the gain of this amplifier that we have made. So R1 and RF are two parts of the bridge, and they are connected in the rest two arms as shown here. So this complete diagram is will be used in the analysis. The total phase shift around the circuit must be 0. This we know that total phase shift must be 0, which is criteria for oscillation. So this condition occurs only when the bridge is balanced, that is at resonance. So in order to find that when will bridge will be balanced, we'll be finding its condition and the frequency of the oscillation. So these are two things that we have to calculate, and we'll calculate it with the help of above diagram. The total phase shift, how total phase shift is 0? Because we had already discussed that in this non-inverting amplifier there is no phase shift, and there is no phase shift here also in the feedback network. So the total phase shift in the circuit is 0. Now we'll calculate the frequency and the gain in the following manner. First of all, we'll take only the feedback part of the Wien bridge oscillator, and we'll replace all the capacitance by their reactances as we had done in phase shift oscillator. So this is lead lag circuit, and C has been replaced by its reactance. So this is 1 upon j omega c, and this is 1 upon j omega c, and the two ends have voltage Vf and V0. So we'll first calculate Vf. So Vf is very easy to calculate. We can calculate it by the help of voltage divider rule. So how can we calculate Vf? Vf is the voltage across the parallel combination here, and V0 is the voltage across these two ends with respect to earth. So first of all, by the help of voltage divider rule, we know Vf is always a part of V0 multiplied by the impedance of the circuit. So how can we calculate it? If we term this impedance as Zp, total impedance, and this impedance as Zs, then we can write Vf is equals to Zp, that is the potential, that is the impedance across which we are calculating Vf, Zp into V0 upon Zp plus Zf, as by the definition of voltage divider rule. Now what is Zp? Zp is the parallel combination of R and 1 upon j omega c. What is the parallel? How can we calculate parallel combination? We can write here in this way: R plus 1 plus j omega cr. This I have written by taking LCM. Again, the Zs is the series combination, so R plus 1 upon j omega c. Again I have taken LCM and I have obtained this value. Now we'll be putting Zp and Zs in the above equation. So when we put Zp and Zs in the above equation, we get something, this very large equation. Now what we require, we'll be simplifying it. So for simplification, we'll take LCM of these two terms and write it here in this manner: 1 j omega cr plus 1 plus j omega cr whole square whole upon 1 plus j omega cr into j omega c. Because this is in denominator, we'll invert it and we can write in this manner. Here 1 plus j omega cr cancels from this term, as you can see, and finally we obtain j omega cr V0 whole upon 1 plus j omega cr whole square plus j omega cr. So this is Vf in terms of V0. Now why we have calculated this? Because with the help of this we can calculate B. Why we want to calculate B? Because we'll be satisfying the Barkhausen criteria that says that AB should be greater than equal to 1 for oscillations. So what will be B? B will be Vf upon V0. So Vf upon V0, this is Vf upon V0. Now again I have opened this whole square and I have obtained this term. So finally by solving it, I can obtain j omega cr. This will be minus, because j square will be minus omega square c square r square plus 1, and these two terms add up to 3 j omega cr. So this is B. Now we have already calculated B. Now we'll be taking the op-amp part. So in op-amp part, we know that we have taken non-inverting amplifier configuration, and for the non-inverting amplifier configuration, we know the gain of the circuit is always AV is equals to 1 plus RF upon R1. where RF is the feedback resistor and R1 is the resistance in the non-inverting end at the input. So we have A and we have B. Now we'll be applying the required condition for oscillation, that is AB is equals to 1. So putting the value of A and B, we get this thing, this equation we get. We'll be cross multiplying it. We'll not disturb 1 plus RF upon R1. We'll simply cross multiply this term. So in turn I get somewhat like this equation. Now here I can see from left hand side and right hand side both imaginary and real parts are there in the equation. I'll be equating real and imaginary parts from both the sides to obtain the condition for oscillation and frequency of oscillation. So first of all, I'll be equating this equation. I'll be equating both the real parts on both sides, the coefficients of real part. So here this is everything is multiplied by j, so there is no real part here, so this will be 0. I have written here, and from here you can see 1 minus omega square r square c square is real part, so I have written this. On solving I get omega square is equals to 1 upon r square c square, or omega is equals to 1 by rc. In terms of frequency, I can write 1 upon 2 pi RC. If I put the value of 2 pi, 1 upon 2 pi, then I get F naught is equals to 0.159 upon RC. So this is the frequency of the oscillation at which this Wien bridge oscillator will oscillate. So the frequency of the oscillation entirely depends on R and C, the combination of R and C. Now we'll equate the imaginary part. So on equating the imaginary part, I get 1 plus RF upon R1 into omega RC on one side, and on the other side I get 3 RC omega. So this I have equated here. Now as you can see, this thing gets cancelled out, and I get RF upon R1 is equals to 2, or RF is equals to 2R1. So this is the condition required for sustained oscillation. If resistors are taken equal in value and the capacitors are equal in value in the reactive leg of the Wien bridge oscillator, in that case, at this frequency, the gain required for sustained oscillation is given by A equals to 1 by B equal to 3, or 1 plus RF upon R1 is equals to 3, or we can write RF is equals to 2R1. So this all these things are written in separate way, but their meaning is same. This is condition required for sustained oscillation. So this was all about Wien bridge oscillator. I have not explained this part. I have written here, but I have not explained because I have already explained this part while we were discussing transistorized Wien bridge oscillator. So this you already know. This same thing has been used here also. So this was all about RC oscillators. So now in this chapter we were discussing oscillators of two types. Broadly they can be divided broadly into two parts. One was sinusoidal oscillators and second was non-sinusoidal oscillators. So in sinusoidal oscillators we had again further classified into three parts, that is LC oscillators, RC oscillators and crystal oscillators. So we have already discussed LC oscillators. Two types of LC oscillators we have discussed, Hartley and Colpin. And in RC oscillators again we have discussed two types, Wien bridge oscillator and phase shift oscillator. Crystal oscillators are not in our syllabus because we have already discussed crystal oscillator in our UG classes. Now we'll be starting non-sinusoidal oscillators. So what are non-sinusoidal oscillators? First of all, we'll be discussing the general topic, and then we'll discuss different types of non-sinusoidal oscillators. So first of all, you must remember, what do you mean by non-sinusoidal oscillators? So non-sinusoidal oscillators are those oscillators that produce waves that are other than sine waves. Non-sinusoidal oscillators mean that they will produce either square wave or triangular wave or any other type of wave that cannot be termed as sine wave. Their different name is also sometimes they are also called multivibrators. So we'll be discussing multivibrators in detail, and again how they are made, how they work, and what is the basic principle behind these multivibrator and where they are used. So all this we'll be discussing here. So today I'll be discussing simple multivibrator. What do you mean by a multivibrator? How many types are there? And then we'll be taking all the types of multivibrators one by one. So multivibrators are non-sinusoidal oscillators, and if we classify them broadly, then they can be classified into three parts. First is a stable multivibrator. Second is one minute. First is a stable multivibrator. Second is monostable multivibrator, and third is bistable multivibrator. So we'll be discussing all three types of multivibrators in detail. Now today I'll tell you what is a stable multivibrator and what is the difference between the three. So a stable multivibrator is a non-sinusoidal oscillator that produces square wave. But a stable multivibrator, in case of a stable multivibrator, no state is a stable state. There is no stable state. We get square wave continuously depending upon its time period. Now for monostable multivibrators are again non-sinusoidal oscillator that produce square wave, but they have one stable state and one state is quasi-stable. That is, if multivibrator comes into a stable state, then it will remain in that state and will change the other state only when it is triggered. Quasi-state is a non-stable state, and after some time again multivibrator switches to stable state. The third category is the bistable multivibrator. Now bistable multivibrator is as the name shows, it has two stable state and there are no quasi-stable state. So if it remains in one state until and unless it is triggered by a pulse, and then it switches to another state, and then it remains there only until it is again triggered back to the previous state. So in this way both the states are stable states. It also produces a square wave. It is also a square wave generator. Now we'll be discussing why they are so important and why they are used. But first we'll be discussing a stable multivibrator. So I'll not explain in this lecture. I'll just go through a simple things that are needed to explain a stable multivibrator. First and foremost, a stable means that is not stable. So it again, as its name suggests, that it has no stable state. Both the states are quasi-stables. Now if we go into the definition of multivibrators, then we can define multivibrators are electronic circuits. Those produce non-sinusoidal waveform, rectangular, square or saw-tooth waveforms. A vibrator that generates square waveform without using any external triggering pulse is called a stable multivibrator. It is also called free running multivibrator. Why it is called free running? Because both the states of the multivibrator are not stable. It automatically switches from one state to another state after certain time. So it is also termed as free running multivibrator. And what do we get from what is the output? We get square waveform without giving any input. So that is the basic oscillator principle, that it should not take any input and it should give output. So it gives square waveform without taking any input. This square waveform will have two levels. So here in multivibrator we have because it has a square wave, so if we draw a square wave, you can see that for a square wave we have something like this square wave. So this is square wave. So in square wave there are generally two states. One is upper one and one is lower one. So or we can say it has two levels. If we term this lower level as 0, then it can be termed as something positive, plus VCC. So these are two levels. So in a square waveform we have two levels, 0 and plus VCC level, and for certain time this level this state or level stays, and after certain time it instantly switches and we get the another level or another state. Again is instantly switches and then we get the previous level. So that is the basic square wave. Now all this, how does this square wave is obtained, and what is the basic circuit for a stable multivibrator? This whole thing we'll be discussing in the coming lecture. Thank you.